Hi, everyone. This is Dr. Wiseman. I'm going to go through the slides from Chapter 2 for you as promised so that maybe we can help you understand the material a little bit better, um, uh, and grasp some of the concepts a little more clearly. So if you have any questions, please just feel free to ask me in class. Um, do take notes. I think it's a mistake to try to just take this stuff in. And I have a little more to say about that here in the next slide. So stay tuned and let's get it going. One thing I'm increasingly seeing in students, this is students of all calibers, from the very, very gifted students down to the ones that have the most trouble in class, is this sort of idea that you can just be a sponge, that all you have to do is be present and you're going to learn. And that's not completely untrue. I go to a movie and I'm going to learn something from that movie, and I get home and maybe I'll remember some of it. But I always notice that when I go see a movie again, I see stuff that I didn't remember or didn't see in the first place. And that's the secret, is that the process of learning is not monolithic. You don't just take it in. You have to work with it. I call it playing with the Play-Doh, if you will. Yeah, you can stare at a can of Play-Doh and you can imagine the possibilities. Don't get me wrong. But the act of thinking about the material, trying to understand and apply the material is far more important. And that's why I include this slide. It says respect the process. In this fast-paced world, it's easy to fall into that trap of wanting everything to come easy. A lot of online stuff is fooling you into thinking that you can just get it. And that's not really true in the world. I think you probably have seen examples of this. For instance, I could watch, Peyton Manning play football. That doesn't mean I'm going to go out there and do exactly what he does, because there's so much more to actual learning and mastery than simply sitting passively and waiting for it to happen. So respect the process. All right. This class is the shortcut. All right. This class is designed to help accelerate the learning process, but yet at the same time, we still have to respect the process, the basic processes of learning. You're learning about physiology. Well, guess what? There's a physiology to learning. We can understand the physiology and we can work around it, but at the same time, we are not abrogating or otherwise bypassing what the basic physiology is. So the key here, have patience. Have patience. I know you guys are busy. I get it. I'm busy too. I struggle with it. There are no shortcuts, especially to the shortcut. And then occasionally there's something out there, but let's be real. All right. There are certainly no shortcuts to the shortcut, and this class is, in fact, a shortcut. You have to stay patient with yourself. You have to stay patient that there is a process, and that process isn't always linear and definitely isn't always straightforward and easy. I wish it was, but if it was, then the skills that you're learning wouldn't be valuable. All right. When we respect the process, we give ourselves a chance. When you try to bypass the process, you're less likely to be successful, much less likely. And secondly, whatever success you have may not be sustainable. Okay, especially if the road gets tougher. And you guys are learning about stuff, and it's not going to get any easier from here. So again, this is just I'm not trying to get you down. Don't let me sit here and tell you that you're not going to make it. But what I am saying is that maybe try to shift your paradigm a little bit to understand that you have needs when it comes to learning. It can't just be something that you fit in between lots of other things. Sometimes you have to set aside time. Okay, so let's get going from there. I just wanted to talk about that just for a couple of minutes. Sorry if I'm preaching to the choir, but I think it's important based on what I've already seen in the class. So this slide is one of those slides that reminds me to tell you that yes, there are things that are more important than others. Do we need to know that matter was formed at the Big Bang? No, not really. But it also, the reason we do these slides is to help give you some perspective. It's like seasoning on a slice of lasagna. All right, it just adds to the overall appreciation of what it is you're about to learn. So sorry if it feels like a waste of time. It shouldn't, because finding those connections, especially those unexpected ones, are always a joy and powerful in our lives. I've learned that from experience. One of the really, really cool revelations about being a human or being alive is that we are what we would call an emergent property. If we took our bodies and just broke them down into the elements, we would have all of these different elements in there: carbon, hydrogen, so forth, so forth. By the way, I have a really, really good mnemonic for the really important ones. Yeah, we have some other ones, including vanadium and some other things out there. Chloride is in there. Yeah, that's kind of important. But here's the mnemonic. C. Hopkins Cafe, mighty good. These are the most abundant. C. Hopkins Cafe, mighty good. Carbon, hydrogen, oxygen, phosphorus, potassium, iodine, nitrogen, sulfur, calcium, iron, magnesium. Yeah, you could add chloride in there too. That's in there. Yeah, sodium is in there too. But in terms of the overall mass, the C. Hopkins Cafe Mighty Good pretty much gets us where we need to go. So again, that idea of emergent properties that would not be predicted based on the composition of whatever system you're looking at. This is an example of how wonderful life is, given that we are beyond the sum of the elements that are in our bodies, including water, by the way. And speaking of water, 62%, almost 2/3 of the mass in our body is water. Another big chunk is protein. Now, protein can take a couple of different forms. I could probably go for more than two, but let's start with two. The two are insoluble proteins. These are proteins that are polymers, and so they won't dissolve readily. And we have soluble proteins, and both do very, very important things. The insoluble proteins are often structural proteins, that sort of thing, provide the infrastructure and the form, whereas the soluble proteins do a crap ton of other things. They are enzymes and all sorts of other fun things. They are the doers. Much of what our bodies are doing things, whether it's taking up space and having shape and form and using that form to achieve some kind of an end. A lot of that runs through protein. Some definitions here. Element is basically an atom. Okay, an atom is the smallest unit of an element. It has a given number of protons. Okay, and that's what gives us the atomic number. Like, for instance, boron has a lot more than 5 in that nucleus. It's got protons and neutrons, but there are exactly 5 protons, and that's what we call atomic number. All right, number of protons in the nucleus. For instance, hydrogen, if it's ionized and it's H plus, all it is one big old proton. There's no electrons, no neutrons, not normally. There are some variants out there, but by and large, it's just a proton. In this case, boron would have 5 protons and 5 electrons, assuming it's not ionized. So why do we need to know this stuff? Because you're going to be involved in medicine and healthcare, and you're going to have patients who are undergoing radiotherapy, radioactivity, et cetera, et cetera. You're going to be dealing with ions and osmosis and diffusion, and this all comes about because of atomic structure. Okay. As I mentioned, a hydrogen atom would be one proton, that would be one positively charged proton, and one electron. A lot of the times, though, hydrogen is ionized and all it is a proton, so it's got a positive charge. Neutrons are awesome, but they have no charge. They have mass, but they have no charge. In fact, a lot of what we deal with when it comes to radioactive elements. By the way, did you know this? Potassium, something that we see all over the place, is radioactive. This natural isotope is radioactive. You can take a Geiger counter, stick it up to a banana, and you'll get a reading. All right, that's because it's unstable, and so it's giving off those neutrons, and that's what we call radioactivity. If we have different ratios, like for instance, we can't have carbon unless it has exactly 12 protons. If it's more than 12 or less than 12, it's not carbon anymore. But carbon, for instance, can vary the number of neutrons. There's something about the biological process that will accumulate carbon-14 up to a point. There's something about the way the enzymes do their little thing, and so forth when they're fostering chemical reactions, that living systems will absorb this 14 isotope. So it has more neutrons than protons. And then when that organism dies, that carbon-14 is unstable and giving off radiation in the form of neutrons. And there is a given amount of time that it takes. And that's what we call carbon-14 dating, because we know how fast the carbon-14 will decay. Once something dies, we can basically predict within a few thousand years, maybe even a few hundred, how when that animal or plant or living organism died. All right, that's where this stuff goes. So it's nice to know. It's just nice to know. It's and you will be dealing with this, especially if you're dealing with patients who are undergoing radiotherapy, whether it's radiation treatment or they're taking radioisotopes for certain conditions. Electrons are fun, but electrons can be a little tricky. They're more of the doers when it comes to, when I mean doers, I mean they're the ones that really affect things when it comes to chemical bonds, for instance. And for instance, whether or not something is shiny. Take a look at maybe get a glass of water. Take a break here for a second. Get a glass of water and look at the surface of the water. Notice that it's shiny. When you see a shiny surface, that means that electrons are free to move across that surface. So look at a mirror or something, electrons. Okay. Glowing neon lights, that's also electrons. What you're doing is you're exciting the electrons to a higher state, and when they fall back, they give off light. Now, electrons are negative, and we often abbreviate it as this E with a superscript negative. That's they have a negative charge. It's exactly the negative of a proton. And they are what give us chemical reactions. They can create chemical bonds. You get ionic bonds and covalent bonds and even what we call van der Waals and hydrophobic bonds. And those are all a function of electron movement and interaction. So let's break down carbon a little bit. Carbon has 6 protons, but its mass number is dependent on the number of neutrons. Okay, so if we have a mass number, which is shown here at the bottom, this one is 12. That's because there are 6 neutrons in that atomic nucleus of carbon. It's carbon because it's 6. All right, that's kind of weird to say it that way. Oh, carbon has 6? No, carbon is 6. If it was 7, it would be something else. Okay. All right. Now over here we have 13. That's the mass number. Okay, it's underneath the letter C here. That means that there are 6 protons. It's still carbon. If again that number changes, it changes the letter. All right. And it has 7 neutrons. We talked about carbon-14 a second ago. Unstable would have 8 neutrons. And again, this is just so that you can get through reference material more easily. I'm not going to say that it's going to be something that's somebody's life is going to depend on. You never know. We had Fukushima, we had 3 Mile Island. Okay, we have wars out there, and people have nuclear weapons, and we have cancers, and they get radioactive treatment. So it will show up one way or another. I promise you. So now let's apply this to all of the elements out here, and you can see they have the proton number in the upper left corner. Now, what you don't see very easily, it's hard to see here, but if you look at, let's go back down here to carbon and just look under there. It's just kind of hard to see. You see, it's not a whole number. What it is telling you, that's actually atomic mass, all right? What it is telling you is that there are different isotopes in the world, and the average mass, when you factor in the ratios of the isotopes, is 12.0, blah, 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 okay? It's telling you the average of if you had a pile of carbon, which, by the way, if you had a pile of graphite, you basically have a pile of carbon. You have a pile of coal, it's almost all carbon. There's a few metals in there, arsenic and really nasty stuff, mercury. Ooh. Okay, but in any case, if you have a pile of carbon, on average, you're going to get that amount of mass in every atom. Is it going to be exactly that? No, it might be 12, it might be 13, it might be 14. And so that's why we have this periodic table for a couple of reasons. One, so that you have a reference. So let's say you have somebody who has, who's been exposed to radon. We've heard about radon. You're going to buy a house, have it checked for radon. Okay. What's going on is that there are radioactive compounds down underneath the earth, okay? And what happens is as they break down, they form radon, and that gas percolates up. All right, radon is radioactive. It floats a little bit like helium almost, okay? It's a noble gas. There's a lot we can learn from these tables. And so I understand if it's not directly relevant to your nursing, but this is a wonderful resource for you if you are involved in something that might be important, like barium, for instance. All right, people take barium for certain types of treatments. If they have mercury poisoning, you can look it up. Where is that? It's right here, right next to gold. Okay. And so forth. So again, a frame of reference, general knowledge. I think it's useful. Just understand what it is about the periodic table in terms of what's going on. We've got the atomic number on the left. We've got the symbol, which is a letter, the name of it, and then the average atomic mass given the abundance of the different isotopes in the world. Now let's start putting the pieces of the puzzle together. We've learned about protons. We learned a little bit about neutrons. We learned a little bit about electrons. Putting them together, we've got ourselves an atom, and that's the smallest unit that can still retain the properties of whatever element it is. In this case, we've got 2 protons, which means that this is helium. It's got 2 neutrons, so the atomic mass would be 4. All right, it's got 2 electrons, and those are present in an orbit around the nucleus. We often call it a shell because while these things do have properties of particles, they also have properties of waves. That's hard to wrap your brain around. I still have trouble with it. But what we have is that these electrons oftentimes behave like a force, if you will. They're moving so fast that they can behave both as a particle and a wave, and so that forms a sort of a shell, if you will. That's why we call it a shell rather than just an orbit, like the moon orbiting the Earth. And what's a lecture without a good David Wolf joke? Never trust an atom, they make up everything. That's true. All things are made up of atoms pretty much, unless you're a theoretical physicist. And the things that are not atoms are actually the components of atoms and the subatomic particles. But in any case, thank you, Dr. Wolf. Appreciate the dad humor. Back to the business at hand. When we begin reacting the shells of atoms, they can begin to have behaviors that then give properties to the molecules that are important in life. For instance, we can bond 2 oxygen atoms together, get this O2. We all know what O2 is. All right. Now, one oxygen isn't going to differ from another. All right. The electrons can't go, oh, I like that atomic nucleus better than I like that one. At least when it comes to oxygen, they're identical twins. All right. Electrons will not care. So they're going to share those electrons evenly. And when we get a relatively even sharing of electrons across two atomic nuclei, we get what's called a covalent bond. Now, that said, there are times, for instance, if we don't have two identical atomic nuclei and you have a covalent bond, one of those nuclei can hang on to the electrons a little bit more than the other. Not so much that they can rip those electrons away. That's a different kind of bond. But they're still sharing. It's just that one atom nucleus is a little hungrier for the electrons. We call it electronegativity. But they're hungrier for those electrons, and so the electrons will hover around that other nucleus more often, and so you will get an asymmetric distribution of electrons. Yeah, they're still being shared. They still go back and forth, but that's what we get at what we call a polar covalent bond. In this case right here, the two oxygens are perfectly identical, so you really are a non-polar covalent bond there. But if we have two different atomic nuclei, two different elements, like say we have carbon monoxide, that's a good one, CO. The oxygen is going to hold on to those electrons a little bit more. It's a little more electronegative, which means that it would have more of a polar covalency. So the three chemical bonds to know, one is the covalent, and yes, we have a couple of subflavors of that. Just be aware of those subflavors. All right. Yes, these are strong to weak, and covalents are the strongest bonds. What makes diamond the hardest substance in the world is because the carbon that's in a diamond, it's pure carbon most of the time, unless it's got color, then it's got impurities in it. A pure white diamond has a carbon atom in it that is surrounded by 4 covalent bonds, and that's why it's the hardest, because everywhere that you go out of that carbon is covalent, and covalents are the strongest bonds. Okay. Then we have ionic bonds. Now, remember how I said that some atoms are more electronegative than others? Sometimes that difference between how electronegative a one atomic nucleus is and another is so great that that one of those atomic nuclei is just going to take those electrons and the electrons say goodbye to the other one. That's what we call an ionic bond, because what's happened is the electrons have been removed from the other atom, and so it now has a charge. Okay, it is formed an ion. When we gain or lose charge, and that's whether we gain or lose electrons, we form what are called ions. You want to see ionization in play? Just light a candle and look at the flame. What's going on there is there's enough heat there that you are ionizing the gases, you're ionizing the carbon as it is combining with oxygen. And so you get light and you get heat. But for a moment there, you have that flame, and then it disappears. You see, what's happening is you're creating a carbon dioxide gas. It doesn't have any color. But for that moment, there's enough heat there and enough energy that you get a glowing flame. And that's due to ionization. Okay, so if you have a non-even charge, but you have if the number of electrons is not equal to the number of protons, that's an ion. And if we have enough electronegativity where you pull some electrons away from that other atom, then you have what's called an ionic bond. And it can be pretty strong. It's not nearly as strong as covalent, but yet it is considered a strong bond. The third one here is called a hydrogen bond. All right. Hydrogen bonds have a unique characteristic that I'm really not prepared to go into right now. Where we see hydrogen bonds is what give water its properties. That if you take grab a glass of water and stick your finger in it and look at it and see what it does, that's due to the fact that the molecules of hydrogen and oxygen in the water are behaving differently because of this hydrogen bonding. Super important for things like DNA, super important for protein structure. But it involves hydrogen, and it involves a couple of other atoms that includes oxygen and nitrogen. But for now, we're just going to focus on covalent and ionic. So looking at water here, we've got our oxygen nucleus here. That's formed up of, I think it's 16. Yeah, I think it's 16. And then we have a couple of hydrogen atoms, and that's one proton and one neutron. In any case, oxygen is so much more hungrier for those electrons than those one protons. There's 16 protons in here. There's some other forces at play. Yes, they are sharing electrons. Oxygen sharing one of its electrons with this hydrogen, and in turn, the hydrogen sharing its electron with the oxygen. But it's asymmetric. All right. Yes, it is being shared, and it's not ionic. We're not ionic yet. If it was ionic, it would just rip those electrons, and electrons would be completely over here somewhere. This would be a polar covalent bond. They're sharing the electrons, but they're not sharing the electrons evenly. So not sharing equally, yet they are still being shared. They're still being shared. And one of the reasons this asymmetric, this polar covalency allows for a more negative end and a more positive end, this behaves like a magnet because the electrons are spending more time around this oxygen. That makes this side of the molecule more negative, just a little bit more negative. And this side where we have the protons that are a little bit lonely, so their positivity is showing through. All right, they're a little more positive. This is just like a magnet. This is just like a magnet. You know how you have one end of a magnet and another? That's what this is behaving. And it makes it a great solvent. It can dissolve other asymmetrically charged molecules like this. If they have a little bit of this plus and minus, or a lot of the plus and minus, they can often dissolve in water. Now, the fatty things, what we call lipophilic, the things that are oily, okay, we call them non-polar, et cetera, et cetera. That's great. Let's talk about this in terms of the bonding. Now, carbon has a lot more electronegativity than the hydrogen does, and it will pull on those electrons asymmetrically, and so it's a little more negative here in the middle than the outside. But the thing is that these hydrogens distribute evenly around. They form basically a form of triangular pyramid. Okay? There's a triangle here, and then there's a triangle here. There's a triangle in every plane of this. If we could make this three-dimensional, it would form a tripod pyramid. That's why it's nonpolar, is because all of the charge is evenly distributed around the carbon. There's no one side or another. If we go back and look at water, there's clearly one side and a positive side and a negative side. Here, it's symmetrical in all three dimensions, and that's why it is nonpolar. This happens to be methane, by the way. And very nonpolar. It will dissolve in nonpolar solvents like oil, gasoline, carbon tetrachloride, all sorts of things, because it's nonpolar. And that's why we have, and so polar tends to dissolve in polar, nonpolar dissolves in nonpolar. So things like fats, hydrocarbons, they're nonpolar, got lots of electrons, nonpolar, they dissolve right through nonpolar solutes, but they don't dissolve in water very well. That's why oil and water kind of thing. I've already started to talk through this one. That is, let's say in ionic bonds, what happens is the electronegativity is so different between one atom and another that the one that's more electronegative will literally rip off that electron. Can be more than one in some cases, but oftentimes it's just one. When you have an imbalance between protons and electrons in an atom, you get, or small groups of atoms, you get what's called an ion. Ions are very polar, which is why ions will dissolve in water. Okay, they have an asymmetric They're not symmetric when it comes to protons and electrons. They're either going to have more electrons and be negative, all right, or they're going to have fewer electrons and be positive. And they dissolve well in a polar solvent, especially like water. Okay. Here are some common ions. We've got the sodium that's lost an electron. Okay, it's positive. Potassium's lost an electron. It's also positive. Calcium will often generally lose 2 electrons at a time. Its outer shell has 2 electrons, and so they like to go away. And so we get a 2 plus most commonly. These are very, very common ions in biology and physiology. Very common. We call these things cations, and the rule of thumb is that you have a T here. There's that plus you could think of as a T. Okay, so we have a cation. Okay, that's what we call it, cations. They have a positive charge. Anions, A negative ion. A negative ion. So for instance, chloride has I think it's 7 electrons in its outer shell, and it wants to have 8. So it picks up an electron readily because of energy in those outer shells. And so we'll form this chloride. And we don't call it chlorine, we call it chloride because that infers the ionization. And so this is a chloride anion. Here's a collection of atoms, phosphorus and 4 oxygens. Likes to have a -3 charge. Very, very polar, very, very important biologically. We phosphorylate and dephosphorylate molecules in our bodies, and so phosphate becomes super important for regulation. And then right here, one of my favorite anions, it's called bicarbonate. Now, we often think of as oxygen as being more important than carbon dioxide. We're always trying to get rid of carbon dioxide. Well, I'm going to let you in on a little secret. Carbon dioxide is just as important to life as oxygen. It's just important in a different way. And one of the ways that it's important is it forms bicarbonate, and bicarbonate's really important for regulating pH in our bodies. And we'll talk about pH a little later. And that's why you got to learn about pH. You can't take care of your patients if they're dying of acidosis or alkalosis and you don't know what the hell that means. Okay, that's why we learn this stuff. Okay, because you're going to save lives, and to save lives, you got to understand the universe, and that involves chemistry. So here's a lovely example of an ionic bond. Okay, sodium has that 1 electron in its outer shell. We call that a valence shell, by the way. And I'm not too worried about that term, but in any case, that 1 electron out there is a little bit lonely, makes sodium in its elemental form extremely reactive. You throw sodium into water, you will get an explosion. Okay, it is crazy. All right, done it. All right, and live to tell about it. All right, it wants to give up that electron. It wants to react with something. Chloride, on the other hand, has 7 out here, and it wants to have 8. Don't, it's atomic physics, physical chemistry. Anyway, it wants to have 8, and sodium wants to have 0. Chlorine is very, very electronegative, and sodium wants to give up that. Beware, if reacting with water was bad enough, if you react sodium and chlorine gas, that would be like Hindenburg kind of stuff. Anyway, that sodium will readily give up that electron. It's not there anymore. We lose that entire valence shell. All right, now it's nice and stable, even though it's positively charged. Chlorine, which is now chloride, it is now a -1 because now it's more stable because it's got the happy number of 8 electrons in its outer valence shell. All right. Now, because we've given up that electron, this has a positive charge. We've added that electron to the chloride. These two will bond together, forming sodium chloride, known as colloquially as salt. There are lots of salts in the world that are not sodium and chloride, but sodium and chloride is what we call the canonical salt, if you will. It's the most abundant, I think, on the planet. And so hydrogen bonds, they are weaker. All right. They are weaker. They are much weaker than even ionic bonds. But they are like ionic bonds a little bit because you have an asymmetric molecule here. This is a little bit, this delta, this goofy looking 6 right here with the positive means that it's slightly more positive than elsewhere in the molecule. And we've got this oxygen here, which is slightly more negative, which means like two magnets, they have a bit of an attraction to each other. It's not a super strong attraction, but it is an attraction, and it's an important one. Water would not behave the way that it is, and life would not exist without water. Okay. That's why you'll notice that it's not a solid line. If we look at a covalent bond, we often have a solid line between the two atoms that are reacting. This one has a dot, dot, dot. Sometimes they do dashes, but most commonly it's dot, dot, dot. That is implying, it's shorthand for saying, hey, we've got a weaker bond here, and it's most likely a hydrogen bond. So I would love you guys to go get that glass of water if you don't already have it, especially when you feel comfortable putting your fingers in, because this is great to be able to see this in person. One of the things we look for out in the universe when we send satellites and people to the moon and so forth, and Mars and other places, is we're looking for water, because the water's properties, the emergent properties of water, make it the most important molecule. There's some arguments there, but among the most important molecules for life to exist. We don't believe, at least right now, until we find evidence otherwise, that life would exist without water. Okay, at least life as we know it. So water's properties, it's a great solvent. Okay, it dissolves lots of ions. It can dissolve ions quite readily. It can dissolve salt. Just take some salt and put it in your water. You'll see it disappear even with just a little bit of stirring. Okay, that's because of its polarity. That the hydrogen and the oxygen are asymmetric. They're sharing the electrons, but they're asymmetric. You have a polarity, which makes it a wonderful, wonderful solvent, especially for biological molecules, which are charged often. Cohesion. Okay, so it's possible. I don't think we could do this in an experiment today, but if you had a small test tube of water, just a little bit bigger than a dime, it is possible to float that dime on the surface of that water. Okay. I even have a video. Let me see if I can pull this up. I'm going to, in the next slide, I'll show it to you. I have a video that shows surface tension a little bit. That's the idea of cohesion, that the water molecules want to stick together. Okay. What you will see is that you'll literally see a drop of water bounce off of the surface of water below it. That's cohesion. All right. The water molecules are holding together, and they're also holding together in the water below it. So you have it's like two magnets with the same end pointed to each other. You ever tried to put two magnets together in the same end? They push each other apart. So that water droplet literally bounces for a second off of the surface of the water, and that's due to cohesion. It's asymmetric, which means you can get a kind of a magnetism thing going on. But again, I'll show that in the next slide. Adhesion. Okay, stick your finger in the water. All right, yeah, a few drops will slough off, but your finger's wet, right? Just like if you step in the shower and your hair gets wet and your hair changes its behavior, and the water doesn't just fall off your hair, it has to dry, right? You have to evaporate that water off. That's adhesion. So if cohesion is water molecules sticking to themselves, adhesion is water molecules sticking to other stuff. Okay? And water is a little bit sticky. Allows for what we call capillary motion in trees. I was walking through the jungle in Vietnam last week, and even though it was sunny out, every once in a while there'd be drops of water on you. That's due to the fact that the plants are moving water up through their tubes of their tissue. And in order to keep the water moving, they have to give up some of that water, and they drop it back down to the ground. It's capillary activity. And that's where the water is clinging to another substance, which allows for water to move up a capillary tube under the right conditions. And then lastly, this specific heat. There's actually one more property, but this one here, this means that it acts to resist temperature change. So it will hold on to heat. All right. If you ever take something out of the microwave too soon, like let's say you're microwaving some green beans or something, and you get too close to that steam, when that steam turns to water, it gives up a ton of heat. And that's why steam burns are worse than hot water burns. It's because water resists changing temperature. It can hold on to heat and or it can give up heat in some cases. It's what we call a specific heat is how much energy is required to change the temperature of that compound. And water, that number is relatively high. Oh yeah, this is what I was remembering. I was like, oh, I hope it's not on the next slide. In any case, solid water floats. If solid water, that is ice, did not float, this planet would be frozen over because the water would form ice when it's cold. It would sink to the bottom and then be insulated by the water above it. Okay? So if we had high specific heat, that water would act as an insulator. The solid water would sink to the bottom and the earth would literally freeze over, except for a little itty bitty amount of liquid water at the very surface of the earth. All right. The fact that water is less dense is insane because it floats and can act as an insulator for the water underneath it. So it keeps water underneath it more warm, which is why that the oceans don't freeze over and why we can have things live under the ice. All right. That's so important that we're actually looking at these underwater oceans on Europa and some of these places. Maybe they've got liquid water, may have life. So what we have here is a bit of a sort of a micro animation of how water can dissolve a salt. Like in this case, literally sodium chloride. If you look right here, you can see that the negative pole of this water molecule is kind of up and away while you're surrounding that chloride with a couple of partial positives. That makes chloride a lot more comfortable and thus is able to liberate chloride from the electrical charges of the other cations here, the sodiums that are in this crystal lattice. The same is true in the opposite direction, where if you have a positive cation, the negative side of the water molecule can make that positive cation a lot more comfortable, and so it can disassociate from the crystal lattice as well. And that's basically dissolution. It's the water molecules providing a comfortable zone for these ions to dissociate. So when you have that magical moment where you have things that are dissociating from a solid form into what we call a solution, what you have is you have the solute. In this case, solute in those previous animations was sodium and chloride dissolving into a solvent, which in biology is almost always water. You can do some other things, but that's never a biological situation, or rarely. Okay. Some things are very, very soluble, and some things are not. Certainly for water, like for instance, sugar, salt, those dissolve quite well, but fats don't. And that's because they are less polar and sometimes larger. And if it gets too, if you have too much solute, if you reach the limit on when the solution can handle additional solute, if you change the conditions, sometimes that solute will precipitate out. One particular solute that's incredibly important is the hydrogen ion. Now, hydrogen is just a proton and an electron. It's the smallest element that we know of. And if you lose that electron, all you're left with is a proton, and that's what a hydrogen ion is. So it's incredibly small, but it packs a wallop when it comes to how it can affect biological molecules. And that's why pH is so important. pH is actually an abbreviation so that you don't have to use tons and tons of long numbers. It's an abbreviation, but when we start abbreviating the abbreviation, which is what we sort of try to do, that's where things get kind of complicated. So pH is simply indicating the concentration of these protons in solution, and it can range from 0 So if it had a pH of 0, that means that the entire solution would be made up. It would be a 1-to-1 ratio. So for every water molecule, there'd be one proton, and then that's almost never going to happen. Or you can have 10 to the minus 14th, which is incredibly small. So imagine a decimal and then 14 zeros in front of it, and that's what would mean that it's very, very low concentration. And that's where it comes from. So when we try to abbreviate the abbreviation, then that's where we lose context. But in any case, if we have a pH of 7, that means 1 in every 10 million water molecules, we have a proton. 1 in 10 million. That's neutral. That we call that neutral solution. So pure water generally has about 1 out of every 10 million. If we get a number between 0 and 7, that is, the lower we go, the more concentrated the protons become. I know that's weird, but it's just it's a function of the way it's abbreviated. That is, if we go to 6, that means we have 10 for every 10 million. If we go to 5, we have 100 for every 10 million, and so forth and so forth and so forth. So the lower the number, the more acidic it gets. All right. So the more acidic, a lower number is more acidic. If we get above 7, if we're going between 7 and 14, we call that alkaline or base. That's to say that the proton value is going very, very low, and we have lots of this other ion called a hydroxyl anion. Okay, hydroxyl, HO negative. We have high concentrations of those. When we have 0 to 7, we have high concentrations of the plus. When we have 7 to 14, we have high concentrations of the minus anion. And that means this is alkaline or base. Anything between 7 and 4, above 7 up to 14, that would be an alkaline or basic solution. And every whole number in pH represents a change of tenfold. Okay, so if we had 7, we would have 1 in 10 million. If we had 6, it would be 1 in 1 million. If it was 5, it'd be 1 in per 100,000. 4, 1 in 10,000, et cetera, et cetera. It's a tenfold change every time you do a whole digit. That's in both directions. And so here are some examples of acids. All right, so these are strong acids are generally very low numbers, 1 to 3. Okay, 0 is just absurd. That's not really relevant biologically. But you can see around 1.5 we have stomach acid, and around 2.5 lemon juice. Tomatoes are a little bit acidic. Normal rainfall is slightly acidic. Milk is just a little more acidic. Turns out human blood's actually on the 7.4 range. It's a little bit above neutral. It's a little more basic. And conversely, strong bases run in the 11 to 14 range, including things like bleach or ammonia, things we use to clean surfaces, oven cleaners, etc. Very, very basic, because that strong base can actually destroy organic acids, of which proteins and fats and so forth are a lot of weak organic acids. Soap is up there. You see water, you can see it's a little bit basic. Blood's just a little bit north of pH of 7. Pure water would be a pH of 7. So it has lower H plus, but more OH minus as you go up the scale. So now we're going to add just another layer to this. If we have a strong acid or base, they readily give up a proton if it's an acid or an OH minus if it's a base. That's why we call them strong acids or bases. But a vast majority of compounds don't readily give up a proton or readily give up a hydroxyl, but they still can. That means they are what we call weak acids or bases. That means that they can, under the right conditions, give off a proton and be acidic, or they can, in some cases, they can accept a proton and be mildly basic. And there are different iterations of this, but what we call these things that can give up or absorb protons or hydroxyls, weak acids or bases. And so what they can do is they can actually prevent widespread changes in pH. For instance, here's one of my favorites. That's that bicarbonate anion. It can, you see, it's a minus, but it's a weak negative, and it will readily absorb a proton and become carbonic acid, H2CO3. So it's a mild base in that form. But the carbonic acid can give off a protein and be a mild acid. So they can actually kind of do both a little bit. They prevent sudden, sharp changes in pH. They help keep the pH relatively neutral. I wouldn't say exactly neutral, but they are relatively neutral. They're kind of like a shock absorber for solutions. And our body is full of these buffers just by virtue of the molecules that we have. So it's good to understand what a buffer means. It's a weak acid or a base. It can absorb or donate protons, or in some cases, OHs. So we've been going for a little while here. We're at about 50 minutes. So here's what I'm going to do. I'm going to go ahead and stop right here for now. We'll just end part one because I know your brain's feeling kind of full and there's no need to keep going. So I'm going to actually create a part two video with the remaining slides. We're a little more than halfway through the slides. And so again, write your questions down. Make sure you take your time. Time is the essence here. I know you want to do this stuff fast. But sometimes just slowing down a little bit actually helps you speed up in the long run, and certainly will help your efficiency in terms of learning the material. Anyway, so we're going to break here. Thanks for your time. I hope you enjoyed the presentation, and we'll pick up where we left off in the next video.